Now we're going to look at graphing equations, and we can do this multiple different ways. One way is just plotting points, and that could be okay if we know what the general shape is going to look like. We're also going to look at finding intercepts of our graph and using symmetry to help us graph. So the first question asks, determine whether the points 0, 3, -2, 0, and 2, 7, if they are on the graph of the equation y equals x cubed minus 2x plus 3. So are these points on the graph of? So basically all we're doing is we're substituting in, we're evaluating, plugging in wherever we see a y. Let's look at this first point. We're going to plug in 3. And wherever we see an x in our equation, we're going to plug in 0. And we're going to go in and see, is that a true statement or not? So if I plug in 3, where I see the y, is this equal to? Wherever I see an x, I'm going to put parentheses for now and go back in now and plug in 0. So parentheses cubed minus 2 parentheses plus 3. Put 0 in the parentheses. Where I can see, yeah, 3 is equal to, well, 0 cubed is 0, 2 times 0 is 0, 3 is equal to 3. So 0, 3 is a point on the equation. On the graph of the equation. So do the exact same thing, but now we want to do it with -2 and 0. So if we go down here, and now let's look at when x is -2 and when y is 0. So is 0 equal to -2 cubed minus 2 times -2 plus 3. Well, if we cube -2 times -2 is +4, and 4 times -2 is -8. And so is 0 equal to -8, -2 times -2, so +4 plus 3. 0 does not equal -1. So -2, 0 is not a point on the graph. So same idea, let's try it for 2 and 7. Plugging it back into the equation wherever we see x and y. We want to see if we have a true or false statement. So 7 is our y value. Is that equal to? So we're going to cube 2 minus 2 times 2 plus 3. So 7, is that equal to, well, 2 cubed is +8, -2 times 2, so -4 plus 3. So 8 minus 4, that's 4, and 4 plus 3 is 7, so 7 is equal to 7. And so this is true. And so 2, 7 is also a point. on the graph. So the following example says just look at the graph and find the intercepts of the graph. And so intercepts are the values where we're actually crossing or touching the X and Y axis. And so right here, I can see we have 1 point, so -3, 0. And let's just be even more let's give more detail. Let's tell each which is the X-intercepts and which is the Y. And so if I look at this point here is when X is 3/2, Y is 0. And this point here, we have X is 4.5, so 4.5 and 0 is our Y value. Or if we look at our Y-intercepts, so points that are crossing or touching the Y-axis. So let's go from smallest to largest. So from 0, -3.5, 0, -4/3, and 0, 3. So just notice that for our X-intercepts, look at the value Y. Y is always 0. For our Y-intercepts, right? The value of X is always 0. And so when you are trying to find the X and Y intercepts and you're given the equation, you're going to set the other one equal to 0 and solve for that variable. So to find X-intercepts, there might be more than one, there might just be one, there might not even be any. So to find X-intercepts, you're going to let Y equal 0 and solve for X. If we were asked to find Y-intercepts given an equation, we're going to let X equal 0 and solve for Y. Sorry. Okay, so we're finding the intercepts of the equation y squared minus x minus 4 equals 0. So for the X-intercept, we're going to let Y equal 0. So doing that, we got 0 squared minus x minus 4 equals 0. And then solve for x. Well, 0 squared is 0, so we get this just negative x minus 4 equals 0. So we want constants on one side, variables to the other, because it's a linear equation. I'm going to just add x to both sides just to make that a positive 1x. So I get x equals negative 4. So our X-intercept is at the point -4, 0. The Y-intercept we're going to let x equal 0 and solve for y. So we have y squared minus 0 minus 4 equals 0. So I notice this time I have a quadratic equation, but I also have a perfect square in here. So I could either use my square root method that we talked about last chapter, or we could actually factor this. This is a difference of 2 squares. So I could factor this as y minus 2 times y plus 2 equals 0, set each factor equal to 0, so y is positive 2 and y is negative 2. So if it asks for the points, put it in point form. So our point would be 0, 2, and 0, negative 2. Okay. So let's take a little break. So now we're going to look at some symmetry and testing for symmetry. So symmetry is helpful when we're graphing, because if a graph is symmetrical either across the x-axis, the y-axis, or the origin, basically we have double the amount of the points that we found. So the first definition is up in front of us for symmetry with respect to the x-axis. We say that a graph is symmetric with the respect to the x-axis if for every point xy on the graph, the point x negative y is also on the graph. So we're reflecting this across the x-axis. And so our x value is staying the same, but what's changing is the sign of our y value. And so in order to test for symmetry across the x-axis, that's a test. For symmetry across the x-axis, what we want to do is we want to plug in negative y wherever we see a y in our equation and see if the equation remains unchanged. So to test for symmetry across the x-axis, we're going to plug in, can't spell, plug in negative y wherever you see a y in the equation. So you might have to do some manipulating to show that it's the same. And if the equation remains unchanged, it's the same, then it's symmetrical to the x-axis. Okay. So if it's symmetrical with a y-axis, notice our y values, and you can kind of see an example of a graph here that's symmetrical with the y-axis. Notice that our y values are the same, it's just that the value of our x have changed signs. So definition, symmetry with respect to the y-axis. A graph is said to be symmetric with the y-axis if for every point xy on the graph, the point negative xy is also on the graph. So to test, we're going to plug in negative x wherever you see an x. and see if the equation is the same. So if we can manipulate it to look like the same equation we started with, then we know that it's symmetrical with a y-axis. So if so, symmetrical. Across the y-axis. And one other type of symmetry would be with the origin. So I kind of think of this, if I folded my paper in force, then it would be a mirror image. And so, and if I'm folding it across the x-axis and the y-axis, they would sit on top of each other. And it says definition symmetry with respect to the origin. A graph is symmetric with respect to the origin if for every point x, y on the graph, the point negative x, negative y is also on the graph. And so to test, we're going to plug in negative x wherever we see an x, and we're going to plug in negative y wherever we see a y. And if we can show that the equation is unchanged, then we know it's symmetrical with the origin. So to test, we're going to plug in negative x for x and negative y for y. And if the equation is the same, it is symmetrical with the origin. So let's look at some examples. I don't like how my origin looks. This doesn't matter. Okay, so let me pull up some examples. So the next example, we have y is equal to, in the numerator, x squared minus 9, and that is all over the denominator, which is x squared plus 2. And it wants us to find the intercepts and test for symmetry. Okay, so let's do intercepts just first, because that's what's listed first. So if I'm looking for the x-intercept, intercepts, we're going to let y equal 0 and solve for x. So if I plug in 0 for y, this is equal to 0 is equal to x squared minus 9 all over x squared plus 2. I notice that I can clear my fraction by multiplying both sides by x squared plus 2. Well, anything times 0 is 0. So we have 0 is equal to x squared minus 9. I have a difference of 2 squares, so I notice I can factor that. I could have solved that using the square root method also, and we should get the same results, where we get x is equal to positive 3 and x equals negative 3. So let's look for our y-intercepts. So for the y-intercept, we're going to let x equals 0 and solve for y. Well, by doing that, we get 0 is equal to, I see an x there, so 0 squared minus 9 all over. I see an x there, so 0 squared plus 2. So in the numerator, I'm left with -9 all over 2. So we have a y-intercept. When x is 0, y is -9/2. Or just graphically, to me, if I had to plot this, it would make more sense if this was written as -4.5 or -4.5. So we found our intercepts. Now we want to test for symmetry. Okay, so let's test. Oops. Let me try that one more time. So I'm going to test for symmetry, and we're going to didn't work. Okay, Control C, let me see. I don't think it worked. Paste. Yeah, it didn't work all the way, but we can still do it. Sorry, I should have just written it out. Here we go. Okay, symmetry. So if we want to see if it is symmetrical, let's say with the x-axis. I kind of think to myself, what's happening if I'm flipping it across this x-axis? Well, again, if I'm flipping it across the x-axis, I'm going to plug in -y. For y. And notice if I do that, I get -y is equal to x squared minus 9 all over x squared plus 2. Where if I made that positive y, right, I'd have to multiply both sides of my equation by a -1. And so that would give me y is equal to, let's distribute that -1 to the numerator. So that would give me -x squared plus 9 all over x squared plus 2. And looking at this, this is not the same. This is not equal, this x squared minus 9 all over x squared plus 2. So since they're not the same, this is not symmetrical with the x-axis. Okay, so let's try it with the y-axis. So this is where we're going to plug in. Well, with the y-axis, what's happening is our x value is changing. Y is staying the same. So we're going to plug in -x for x. So we would get y is equal to negative x quantity squared minus 9 all over negative x quantity squared plus 2. But negative x times negative x, if we multiplied that out together, right, we would get positive x squared. So we could rewrite this as x squared minus 9 all over x squared plus 2. This is the same as the original equation. And since it is, that tells me that this is symmetrical with the y-axis. With an origin, we're going to plug in negative x for x and negative y for y. And see if that is unchanged. So going into the original equation, we would have plugging in negative y for y. So we got negative y equal to negative x wherever we see an x. So negative x quantity squared minus 9 all over negative x quantity squared plus 2. I can see right away, I'm going to get the same thing that I had gotten when I plugged in negative y for y. Because notice that, again, when we're squaring a negative, so this is negative y equals x squared minus 9, x squared plus 2. Y is equal to negative x squared plus 9 if we multiply both sides by negative 1, x squared plus 2. And this doesn't equal the original. So this is not symmetrical to the origin. Okay, so we were able to test for symmetry and found that it was symmetrical with the y-axis, but not the origin or the x-axis. And we were able to find the intercepts of that graph. So the next example in front of us, same type of example that we're going to find the intercepts and test for symmetry. The equation we have is y is equal to x all over the quantity x squared minus 4. And so let's look at the intercepts first. So X-intercept. We're going to let y equal 0 and solve for x. So you got 0 is equal to x all over x squared minus 4. We can clear our fractions by multiplying both sides by x squared minus 4. And doing so, we get 0 is equal to x. Okay, so I can see that that's the origin, which means I should find that when I look for my y-intercept, right? So for my y-intercept, we're going to let x equal 0 and solve for y. So we got y is equal to 0 all over 0 squared minus 4. This one's okay because we got 0 on top all over a number other than 0, which is -4. And so this is equal to 0. So we only have one intercept and it's at the origin. Okay, so for symmetry, doesn't matter where we start. So let's just, again, let's start with the x-axis. That means we're plugging in -y for y. So it's -y is equal to x all over x squared minus 4. But if we multiply through by -1, we get y is equal to -x all over x squared minus 4. And this is not the same. So not symmetrical to the x-axis. So if we wanted the y-axis, we're going to plug in -x for x. So we get y is equal to -x all over -x quantity squared minus 4. So y is equal to -x all over, well, -x quantity squared is the same as x squared minus 4. So it's not symmetrical to the y-axis. And then test for the origin. So plug in -y for y. So we get -y equal to, plug in -x for x. So -x all over -x squared plus 2. I'm sorry, not plus 2. That was the other example. Minus 4. Well, -y equals -x all over x squared minus 4. Multiply both sides by -1. We're going to get the exact same thing we had before, or when we started. So we get y is equal to x all over x squared minus 4. So we got back the original equation. So the graph is symmetrical with the origin. Okay, so you're given a graph and you're asked to graph the rest of the function given that it has symmetry. And so let's say we have given this graph and we want to graph the function or the rest of the function. If this is symmetrical across the x-axis. So recall that told us if it was symmetrical with the x-axis, if xy is a point, then it changed our y value. X negative y is also a point. And so 0, 0, changing the y value doesn't do anything. But 1, 1, if I was looking at what point is symmetrical to that point across the x-axis, this would be the point 1, negative 1. Right? If I folded this paper across the x-axis, this point would be lying on top of this point now. This point 2, 4, just changing my y value. X stays the same, would be 2, negative 4. It's right here. And so graphing it would look something like this. What if it was the same graph, but it says graph it if it was symmetrical with the origin? So if this was symmetrical across the origin, that means any point XY that's on our graph, then that's gonna give us the same points that are on the graph, negative X, negative Y, not the same point, but will give us points that are also on the graph. And so 0, 0, changing the sign doesn't do anything. 1, 1 though is going to become negative 1, 1. Oops. Let me just pause. Okay, 1, 1 now becomes negative 1, negative 1. And that point 2, 4 now becomes a negative 2, negative 4. And so just plotting them, negative 1, negative 1, negative 2, negative 4 will be about here. And so if we plotted this paper in fourth, or sorry, folded this paper in fourths across the x-axis and the y-axis, this is what it would look like, a mirror image of that. So given a graph or part of the graph, and given that it's symmetrical across something, you should be able to complete the rest of the graph. Okay, so I was just making sure you guys are able to do the homework. The only other type of example that I saw in there, which is easier than what we just did, instead of giving you half of the graph and telling you to graph it, they just give you 1 point. So if 3, 6 is a point, and we want the point symmetrical, find the point symmetrical, let's say across the y-axis. So find the point symmetrical across the y-axis. So for flipping across the y-axis, the y value is staying the same, but the x value is changing. And so change the sign of our x value, negative 3, 6 would be that point. That would be symmetrical across the y-axis for 3, 6. Okay, so that is 2.2. This is one chapter in this book that we're going to kind of fly through a lot faster than the other sections. So we're going to stop there, but tomorrow, not tomorrow, the next class, we're going to be looking at graphing lines. And so that should be pretty simple. And we should fly through that.